So let's talk about half-life. So we know that these radioactive elements will break down into smaller nuclei, but how long does it actually take for that to happen? Well, that varies depending on the element and the isotope that we're talking about. Half-life is defined as the time that it takes for half of the initial reactants to disappear. So, for example, if I have 100 grams of a substance, how long would it take for me to only have 50 grams of that substance? That amount of time is what we call the half-life. There are a couple of equations that relate to half-life. So if we know the amount of time that has passed, and we know our rate constant, K here is a rate constant, then we can relate the amount of our substance that's remaining and the initial amount. So Ln is a natural log. So if we take the natural log of the amount remaining of our initial amount, that is equal to the negative of the rate constant times the time. If we know 3 out of the 4 variables, we can plug in the 3 that we know and solve for the 1 that we're missing. If you're not given a rate constant, but you are given a half-life, we can calculate the rate constant So the rate constant is equal to 0.693 divided by the half-life. And there is a way to derive this 0.693. We didn't just pull this number out of a hat. I won't go through all the math needed to get to that number, but there is a reason that we use the 0.693. It's derived from an equation, and we've simplified it to this point. But this is all I will require you to use. So let's take a look at some examples here. And before we do that, let's look at what a half-life actually means in terms of how much of our substance is left. So if we start at the very beginning, before any of whatever substance we have has started decaying, none of it has decayed yet, and we have 100% remaining. After one half-life, only half of it remains, so 50%. After 2 half-lives, only half of what we had after the first half-life remains. So 50 divided in half is 25%. After 3 half-lives, we would have 12.5%. After 4 half-lives, 6.25%. And we can keep going from there. So half-life is independent of how much material we started with. After one half-life, we will always have half of whatever amount we started with. It's also independent of temperature, and it's independent of the chemical form of the element. It doesn't matter whether it's a solid, liquid, or gas, half-life is always going to be the same amount of time for that particular isotope. So let's look at an example here. The half-life of zinc-71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes has elapsed? Now, there's a couple of ways to approach these types of problems. We can use our equations, or sometimes if we're doing an exact number of half-lives, and we're only doing a few half-lives, so I'd say probably not more than 5. If you want to keep going past 5, you can. But we do need to have an exact number of half-lives in order for this approach to work. And if we have an exact number of half-lives, we can save ourselves the work of having to go through all of those equations if we just look at what half-life actually is. An amount in grams. So after one half-life has passed, this isotope of zinc has a half-life of 2.4 minutes. So after 2.4 minutes has passed, I would have half of what I started with. So half of 100 is 50. After two half-lives, so two half-lives would be, since each half-life is 2.4 minutes, two half-lives would be 4.8 minutes, and I would have half of what I had after the first half-life, so 25 grams. After three half-lives, 3 times 2.4 is 7.2, which is exactly what I was looking for, and after the third half-life, I would have half of what I had after the second half-life, which would be 12.5 grams. Now, after we do the equations, you can come back and try to do this one with the equation, and you should get the same answer. So it's a little bit less work to go through this way if we happen to have an exact number of half-lives, and we only need to go through 2 or 3 half-lives. Now, we don't always get fortunate enough to be looking at an exact number of half-lives. So, for example, here I have cesium-131 has a half-life of 30 years. After 120 years, about 3 grams of a sample remains. What was the original mass of the cesium-131 sample? So actually in this case, I do have an exact number of half-lives, but what I need to know is the original mass, not how much is left after so many half-lives. So let's look at how we would solve this. If you look back at the two equations, you'll notice the first equation that relates the initial amount and the amount remaining requires a rate constant, which we call K. We're not given the rate constant, so we have to figure out what the rate constant is. We can calculate the rate constant by taking 0.693 divided by the half-life. So if I take 0.693 and I divide that by 30 years. So if you put that into your calculator, 0.693 divided by 30, I come up with 0.0231. And since years was on the bottom, the rate constant has units of inverse years, or years to the -1. So now I can use my equation that will let me figure out what the original mass was. So if I plug in, I know that I have about 3 grams of my sample remaining. And I'm going to plug in my rate constant that I just calculated. And I was told that this is after 120 years. So then what I'm going to do is I'm going to take the 0.0231 times 120, so that I'll have a little bit less to write here. So 3 grams. And if I multiply these two together, I get -2.772. So now I need to get, somehow I need to get N sub O, which is my initial amount, by itself. The way that I get rid of a natural log is by taking the inverse of a natural log. 3 grams over N sub O. And the inverse of the natural log is by taking E. Now this is not the same E that we use for exponents. You should see a button on your calculator that has natural log, and above it you will see an E. So you might have to hit the second key to get this E. But we use the E that's the inverse of natural log, e to the -2.772. And I'm going to add another slide in here. If I put e to the -2.772 into my calculator, I get 6.25 times 10 to the -2. So then I need to rearrange this algebraically. And then I'm going to divide both sides by 6.25 times 10 to the negative 2. So if I do that, I get 3 grams divided by 6.25 times 10 to the negative 2. That gives me 50 grams. So initially, I started with 50 grams here. And I would have, after all of these half-lives, gotten down to 3 grams. Okay, let's take a look at another example here. Phosphorus 34 has a half-life of 14.26 days. What percent of the sample remains after 35 days? So again, I need to figure out my rate constant before I start trying to use the other equation. So I have K equals 0.693 divided by and my half-life is 14.26 days. So if you put into your calculator 0.693 divided by 14.26, you should get 0.0486. And since my half-life is in days this time, my unit for my rate constant is going to be inverse days. So if I take the natural log and I'm going to plug in, I know what K is now because I can solve for that. And I'm talking about 35 days for my time. So if I multiply .0486 times 35, I get negative 1.70. And then again, I need to get n over n sub O by itself. So I do that by taking e to the 1.70. And if you put that into your calculator, I get 0.183. So that's in decimal form. The question asked me what percent. So to get a percent, I need to multiply this by 100. So I would have 18.3% left. Okay, let's take a look at one more example here. How much of a 40-gram sample of uranium-235 is left after 10,000 years if the half-life is 7.04 times 10 to the 8th? So again, I'm going to solve for K first before I try to plug into my other equation. And my half-life is 7.04 times 10 to the 8th years. So if you plug that into your calculator, you should get 9.84 times 10 to the negative 10th. So now I can plug in to my equation, and I start with a 40-gram sample. So this time I want to know how much remains. Times 10 to the negative 10th years. And we have 10,000 years that have passed. So if I take the natural log of n over 40 grams, and if I multiply 9.84 times 10 to the negative 10th times 10,000, I get negative 9.84 times 10 to the negative 6th. And then I want to get 40 by itself, so I'm going to take e to the 9.84 times 10 to the negative 6th. And if I do that, and so that I don't have to write all those numbers out, I'm just going to e to the negative 9.84 times 10 to the negative 6th. And if you plug that into your calculator, you should get 39.9 grams. So if we look at how much we started with and how long the half-life is, the half-life of uranium-235 is 7.04 times 10 to the 8th. So that would be 1, 2, 3, 4, 5, 6. So that would be 704 billion years. And we're talking about after only 10,000 years. So not very much is going to decay. So it makes sense that our answer is close to our original amount. Okay, so what we've been talking about is decay, where we split nuclei. The term for splitting nuclei is nuclear fission. In nuclear fission, we split a large nucleus into a smaller one, and we also release some energy. So energy is released because what happens is that the sum of the masses of the fragments is actually less than our original mass. So that original mass doesn't just disappear, it's actually converted to energy. So we can convert between matter and energy, we just can't create or destroy matter and energy. It has to go somewhere. In this case, the matter turns into energy. So the missing mass, which in a lot of cases only accounts for about 0.1%, has been converted into energy. And we can actually determine the amount of energy using Einstein's equation, E equals mc squared. So if you plugged in the amount of mass that we lost, and we multiply that times the speed of light squared, and the speed of light is equal to 2.998 times 10 to the 8th meters per second. So if you square that number, you get a pretty big number, which means you can get quite a bit of energy out of a small amount of mass. What happens a lot of times is when we use something like uranium-235 and we bombard it with neutrons, the product of that reaction, if we go back to the previous slide for a second, we get some smaller nuclei, but we also get neutrons out of it. And those neutrons will actually cause more reactions to happen. So we actually get what we call a chain reaction going, where that first fission product produces some more neutrons that can be used to initiate more reactions with uranium-235. So the reaction actually becomes self-sustaining, that it will just keep going, producing more neutrons, which can in turn react with more uranium-235, which in turn produces more neutrons, which in turn reacts with more uranium-235, and we just keep going. So in a nuclear reactor, what we do is we have a nuclear chain reaction in a controlled environment. So it's initiated within a controlled environment and sustained at a steady rate. So it's different from a nuclear explosion where all of that would occur in a split second. We have this reaction controlled and sustained at a steady rate, and we can use that energy and the heat that's produced to provide electricity. So the opposite of nuclear fission is nuclear fusion. Instead of splitting the element, we actually unite two light nuclei. So what happens is that the masses of the two nuclei fuse into a single nucleus, and we get a greater, the masses of the original two nuclei is greater than the mass of the nucleus formed. That difference gives us an amount of energy that's released. So, for example, if we take hydrogen nuclei, we can get helium and some energy left over. The difference is eventually released as energy. So the potential for fusion is great because we can get a lot of energy from fusion. And one thing to note, we use uranium a lot for fission, but the uranium supply is somewhat limited, whereas we can get quite a bit of deuterium, which is a hydrogen nuclei that has a mass number of 2 rather than a mass number of 1. The problem with fusion is that we need really high temperatures to do it, and that really high temperature is pretty difficult to achieve. So we just don't have fusion reactors currently that can maintain those temperatures. So this wraps up nuclear chemistry. So we will stop here, and I will see you in class.